Let's apply the Bernoulli equation to an example of a textbook problem. I have here a water tank with a small hole near the bottom at a depth of 2 meters from the top surface. What is the speed of the stream of the water emerging from the hole? Here's a picture of that. A couple of assumptions noted on this picture that are really important for us to notice. In fact, my pro tip for solving Bernoulli's problems is try to figure out all of the quantities in the equation that you can assume to be zero. The first one is that this wide top to this container suggests that that fluid level is moving very slowly compared to the fluid exiting the tank. So we're going to assume that that velocity of the fluid at the top level is zero. Now there's a pressure at the top of the water, and there's a pressure of the water as it exits the tank. Okay. Let's take a look now at how we might solve this. So there's a note here that both the top and bottom of the container are open to atmospheric pressure. That means the pressure on the top level of the surface of the water and as it's exiting the container, both open to the atmosphere. Each of them is at atmospheric pressure. That'll be relevant in just a moment. And the velocity up at the top, already discussed that, that's zero. I've written out the Bernoulli equation at the bottom of the screen here. Right? Just copied it down exactly as is from my last video. Now I'm going to start figuring out what's zero and what numbers I do know. So the next thing I've done is I've gone through and I've said, well, pressure 1 equals pressure 2. Boom, boom. They're going to subtract to zero, so I'll just take them out of the equation. We know that the velocity at the top of the tank is close enough to zero, negligible velocity. Let's take that term out. Boom, whole term goes away. All right, now simplifying and rewriting, I've got density, gravitational field strength, height 1, equals the kinetic term plus the gravitational term from Bernoulli's equation. Which of these values do we know and what are we solving for? Let's see here. How fast, what is the speed of the water coming out of the pipe? I want to know velocity 2. Sorry, that's not velocity 2. I want to know velocity 2. I've rearranged this equation here before I put any numbers in it. So your mileage may vary which way you go. But check out the equation. Solving for velocity 2, I get velocity 2 squared equals all of this. Okay? Take a moment, make sure that that math checks out. So let's see here. The densities go away. Solving for the square, so square root of 2, gravitational field strength, change in height. So we were told in the problem that the spigot is 2 meters down from the top of the container. You see that here in this picture. What's interesting is I don't care what the overall depth of the container is, just how far that liquid level has to go down in order to exit the container. 2 meters. Gravitational field strength is a constant. Here on Earth, we know that. What's crazy about this problem is all of that really long Bernoulli's equation at the beginning simplified down to root 2, times 9.8 times 2, the change in depth. That amounts to 6.3 meters per second. Thanks for watching. I've got a little note here at the bottom of the page. When do I apply Bernoulli's equation? Look for problems about moving fluids that are changing heights. Good luck and happy problem solving.